Hello, and welcome to Spectral Methods in Machine Learning. My name is James Requeima, and I'll be giving this series with my colleague, Wessel Bruinsma. And today we're going to be talking about some of the concepts and tools from machine learning and spectral methods that we're going to use in the rest of the series. So let's start with probabilistic modeling. As we know, modeling is central to science. It allows us to gain insights into real-world phenomena, make forecasts, and test hypotheses. But it's important for us to be able to say something about how certain we are of these models, rather than just trust their predictions or have no way of actually quantifying our certainty in them. So the probabilistic approach to modeling does exactly this. It expresses the uncertainty with the language of probability theory. And in these talks, we're going to use Bayesian modeling and probabilistic approach to modeling as being synonymous. Basically, they both use probability theory to estimate model parameters from data, make forecasts, and test hypotheses. So Bayesian modeling uses probability theory, and it uses two main rules from probability theory. So the sum rule and the product rule. So these are some basic probability theory rules that you may be familiar with. And importantly, these yield Bayes' rule, which is an important formula for us in probabilistic modeling because it tells us how to update our certainty about any aspect of our model. So for example, if we have a model which is parameterized by theta, and we observe some new data x, then we can say something about our certainty of these models, these parameters theta, in the presence of this new data. So here, the prior, P of theta, represents the belief about our parameters before we observe any data. And our posterior, P of theta given x, is a belief about theta after observing some data. So, we don't have to think about how to update our parameters. This formula explicitly tells us. So there's some criticism about Bayesian modeling, and I want to just clear up some misconceptions. One criticism would be that, before we do any updating or before we actually observe any data, we have to explicitly specify our prior beliefs over our parameters or any aspect of our model. This is true, but I'm not sure that P of theta should be viewed as an specifying P of theta should actually be viewed as a problem with this approach to modeling. In fact, I think we should view it as explicitly stating our assumptions about the model. No matter what we do in modeling, we're going to be making assumptions. And one of the benefits of the Bayesian approach is we explicitly make these assumptions clear at the beginning. We state all of our assumptions that we're going to be making rather than hiding them. And when we start from that viewpoint, we can actually quantify all of our assumptions that we're going to be making. So another common objection is that it doesn't really make sense to treat model parameters as random variables. There's this belief that there may be one set of true model parameters that we're trying to estimate. So there's nothing random about them in the real world. They actually exist and have some values. But this is also a misunderstanding. It's not that Bayesians believe that these parameters or some quantity you're trying to estimate in the real world is random. It's just sort of a misnomer because we're going to use the language of probability theory to quantify our belief about those parameters. So whether or not they're fixed, it doesn't really matter to us. We're just going to use probability theory to quantify our beliefs about what we believe these parameters to be. So the nice thing is in this framework, modeling basically breaks down into a simple two-step procedure. So we start by writing down our assumptions in the language of probability theory. And once we've done that, if we observe some data, we use these rules of probability theory, in particular Bayes' rule, to make inference about unknown quantities in the model. So a nice aspect of this procedure is that it decouples modeling and making predictions, which often become entangled with when our goal is to make forecasts. So we build the best model that we can using the data that we've observed and make any inferences about things in the model which we may be uncertain about. And then we use this model to make predictions once we've done this. So I talked a little bit about the approach to modeling, but I'd like to talk about a tool that we often use in probabilistic modeling called the Gaussian process. So Gaussian processes have been successfully applied to a lot of contexts. They can be used to automatically discover structure and signals. They've been used as state-of-the-art regression models. They provide data-efficient models in reinforcement learning, which is a pretty popular field in machine learning right now. And they've been applied to probabilistic numerics, examples such as optimization, and in particular Bayesian optimization and quadrature. So what is a GP? Well, let's talk a little bit about it before we look at the formal definition. You may have heard of a neural network, right? Another model that's very popular in machine learning right now. And a neural network is an example of a parametric model. So a parametric model has a finite set of parameters and fixed complexity. So what that means is once we've specified our model, the complexity of our model is fixed. It can't change at all after that. And this is different from a Gaussian process. A Gaussian process is an example of a non-parametric model. So we don't actually have to write down a set of finite parameters beforehand. And the nice thing is that the model complexity grows as evidence is accumulated. So unlike a neural network where if we specify a very large neural network and we don't observe much data, then this data has a potential to overfit because we've specified a really complex model. And once we've observed enough data to, in the model's eye, successfully estimate the parameters of that model, well, we can't actually increase the complexity of that model at all. It's fixed at what we wrote down initially. And Gaussian processes, they don't do this. They can learn complex functions if we see more and more evidence, and the model can get more and more complex as we see more and more data. And it makes them robust to overfitting because if there's not much data, well, it doesn't start with an overly complex function. It uses its simplest explanation possible to explain that data. So one nice aspect of GPs, which are Gaussian processes, is they define a distribution directly on the space of functions. So we're going to, again, be talking about probability distributions, and they're able to put a probability distribution on the space of functions. And they can be thought of infinite dimensional generalization of a multivariate normal distribution. So you essentially can view it as a very large Gaussian, infinite dimensional Gaussian. Now, when we're using a GP, we have to make two modeling decisions. And as we said, when we're doing probabilistic models, we have to explicitly state our assumptions. So what we're going to have to do is we're going to have to decide on a mean function and a covariance function, or a kernel for the GP. And what these functions are going to do is they're going to specify the prior distribution on the space of functions. This is going to quantify our beliefs about the form of the function that we are modeling before we've seen any data. So if you're fairly certain about the form of the function you're trying to estimate, you can incorporate that into the mean and kernel of for the GP that you're using. And if you're fairly uncertain, you can do the same thing. You can say, well, I'm not too sure about what this function is going to be, so let me choose a mean and kernel that are fairly uninformative. So let's actually look at what a GP is. So as I said before, a Gaussian process is an infinite collection of real valued random variables. So you consider every point on, say, a function as a random variable, and you can index that set as t. So If we're, say, defining a function on the real line, the indexing set would be R, and at every point on the real line, we consider the function value to be a random variable. And a GP works in such a way that each of these values, each functional value at any index point, are jointly distributed according to a Gaussian. And any finite index set in particular is distributed according to a Gaussian. So if we were to do this, then what has to happen is any way we condition this GP has to be consistent. Meaning, if we take two indexing sets and we look at the distributions implied by that, they have to agree with each other. So another way of saying that is they have to respect the rules of marginalization and permutations of the variables. So if you look at this plot that I've shown here, and let's consider these grid lines, these vertical grid lines, to be places where we're indexing the Gaussian process, then the y values at these locations, the probability distribution over those y values is a multivariate Gaussian. So how does it work? Well, the mean function and the kernel of a Gaussian process specify the mean and covariance of any finite dimensional distribution in the following way. So if we take some finite indexing set, then the y values, the functional values, I should say, at these points are distributed according to a normal distribution, where the mean at those points are given by the mean function, and the covariance is given by the kernel function at those points as well. So we can see the variance of the y values at location t1 is given by a value in the kernel at t1, and any of the covariance values, say the covariance of the functional value at tn and t1, are given by the kernel at those values. So in order for this to make sense, the kernel must be such a function such that when we do this procedure, if we were to evaluate the kernel at all these points, we need to get a valid covariance matrix, i.e. a positive definite matrix. And such a function with such a property we call a positive definite function. So we're going to use this notation. We're going to say if f is sampled from a GP with mean m and k to mean exactly that. This is what this notation means. It means f is sampled from a GP with mean function m and kernel k. Now, we can, and one nice thing about a GP is we can handle noisy observations as well. So let's say y1 to yn are observations of some unknown function, but we know that our observations are contaminated with some noise. One common assumption to make, and again, we want to be explicit about our assumptions, is that let's model this noise with IID samples from another Gaussian with mean 0 and variance sigma squared. And in this case, the generative model, or the way that we say yt is generated, is by the sum of samples from our Gaussian process and samples from this noise process we put on top of that, which is written here. Now, the nice thing is this, of course, defines another Gaussian process over y of t. Now, if we want to figure out, well, okay, fine, I've specified a prior distribution using a GP, that's fine, and its mean and variance are specified by m and k. But if I'm given some new data and I've observed these y values, how do I update my mean and variance, or in other words, my Gaussian process, or the Gaussian that's defined at any new points that I want to index? Well, we basically just use the rules of probability to compute these things. I won't go through the derivation, but basically what I've written here specifies the posterior mean and variance, or covariance, for the new GP on F. So what this means is basically the posterior mean at any location t is given by the kernel evaluated at t and this vector capital T, which I've specified here, at all the observation points. And again, that's what I mean by this capital T here, plus sigma squared I inverse times y. And again, similarly, the posterior kernel at any two new points is updated in a way. And basically, you can get these by just going through the probability rules that I wrote before, the sum and marginalization rules, sum and product rules before, and using Bayes' rule. Now, this is the predictive distribution for F, which is often useful, but we may want the predictive distribution for Y, and it's essentially the same thing, except we add that sigma squared noise onto our posterior kernel that I've written here. So the derivation of this is not too important, but it's useful to note what the forms of these things are, because we're going to be taking a look at that again later on. Now we can also talk about multi-output Gaussian processes. We don't have to just model a single output value. We can actually talk about GPs which model, multiple outputs. So in this case, we again have mean and covariance functions, but now they're specified by multi-output mean and covariance functions. And again, the mean and covariance are specified by such a mean function and kernel. But you'll notice now that we don't only have to consider the covariance of one of these functional values, but now we have to consider the covariance of all of the outputs as well. So again, similar to the one-dimensional case, we can collect all these outputs into a vector, which we call f of t, and we write that f is drawn from a GP with mean m and kernel k. But this kernel again is we consider it a multi-output kernel. So we talked a little bit about kernels, but I haven't actually shown any examples of a kernel. There are many different kernels we can use, and each kernel comes with its own set of assumptions. But I thought it would be a good idea to take a look at some in particular. So one commonly used kernel is the exponential quadratic or squared exponential, and it's given by this form. So, basically you can see if we want to compute the covariance of the function value at t and t prime, it's given by this exponential here. And basically it says that as t and t prime get closer, we can see the value of this exponential gets closer and closer to sigma squared. And these parameters here of our kernel, sigma squared and L squared, are known as the variance and the length scale. Now, we can modify the squared exponential kernel by, instead of saying the length scale is independent of the input dimension, right? If t is a vector, then L is independent. We just take a vector norm here. But we can say that we can actually specify a different length scale for every dimension and modify our kernel this way. And this is said to have automatic relevance determination. And the reason for that is because every dimension now has its own unique length scale. And when the hyperparameters are learned, the kernel can learn to scale the data independently on every dimension. So if we learn to have a very small length scale in a particular dimension, then what will happen is we'll say, well, in that dimension, the value in that dimension doesn't actually affect the covariance very much unless they're really, really close together. And alternatively, if we make the length scale very, very large, we do the opposite thing. And this length scale, in GP terms, we say like it affects the wiggle in dimension D and determines how the Gaussian process can extrapolate away from the data. So looking at some particular length scales, here's some samples from the distribution implied by a Gaussian process. So some using different length scales. So we can see that your length scale is very small, then our samples may be very, very wiggly. And if we say our length scale is very smooth, then we see that our functions change if our length scale is large, we see our functions change very smoothly. They don't wiggle very much because the covariance properties are stronger across longer distances. So in the notes we've supplied, and here I list some other common kernels you can look at, and basically here's the functional form for the kernel, and importantly, the assumptions that that particular kernel makes about the functions that you're modeling. So if you don't believe, for example, that your function is smooth and wiggles on many leg scales, then the rational quadratic would not be a good choice for you. So, the fact that a Gaussian process is called a non-parametric model, we shouldn't be confused with the fact that there are these parameters, which we call hyperparameters, these parameters of the kernel. And we're not going to get into why it's called non-parametric when there actually are parameters. That's a long discussion, but basically this is the way the terminology works. And so these hyperparameters of the kernel, like the length scale or the variance, for example, how do we actually learn them? Well, one way of learning them is to use maximum likelihood estimation. So basically, given a set of parameters that I could choose, I can evaluate the likelihood or the probability of observing that observing that data under my model. And I'm going to select the set of parameters that actually maximizes these values. Now, this is often called it's called maximum likelihood, or sometimes called maximum marginal likelihood in terms of GPs, which is a bit confusing because it doesn't seem like we marginalize anything, but we actually have marginalized the latent functions. You notice there's no F's here. We're talking only in terms of Y, so that's why it's called the marginal likelihood. And sometimes it's also called the model evidence. Now, why would we do this? Well, this is a principled way of selecting these model parameters, or any modeling assumptions that we have, to be honest. And it follows, it tends to explain the observations in an appropriately simple way. So in selecting the simplest explanation that explains our data, essentially, which we call Occam's razor. So I'm just going to take a second to look at that. So suppose we have on the left-hand side, here's my marginal likelihood, and I've wrote M of M, so some modeling assumptions. This could be a kernel we're selecting, or the parameters of a kernel, or any modeling assumptions we've made here. And just abstractly consider all possible data sets here on the x-axis. And given that particular assumption, here's the density of all of those data sets, or the marginal likelihood. So if we choose a model that's too complex, then what's going to happen is we're going to spread our mass over all possible data sets really, really thin. And so the marginal likelihood is going to be really small. On the other hand, if we choose a model that's too simple, then we're going to place all of our mass at a small location. It'll explain some data sets extremely well, but maybe not our data set particularly well, and we're going to get a very small value. And if we have a just right fit, then we're going to be at the location where we get a relatively high density for our particular data set. And it explains some other data sets, but it doesn't spread our mass out too thin, so we get a just right fit. And so this is just a way of motivating our use of the maximum marginal likelihood when we're choosing any modeling assumptions to do with a GP. So I want to talk a little bit about deep GPs, or deep Gaussian processes. They're going to come up a little bit later on in the lectures. And they have a very strong connection with deep neural networks. So as you may know, deep neural networks have impressive performance on pattern recognition tasks in applied domains such as computer vision and natural language processing. And in particular, they have very impressive performance on tasks where there's a lot of training data present. However, it's kind of been observed that their performance, if you have a very, very large neural network and you have a small training data set, their performance suffers quite a lot, which makes sense because you've essentially specified in your assumptions a very complex model with not enough data to learn those parameters. So as we've said, they're very large, flexible parametric models. And again, in advance, we need to specify the architecture, i.e. the number of layers we may use, the number of hidden nodes in each layer, the connections, et cetera, et cetera. And once we've done this, as mentioned before, the complexity of the network is fixed. Now, deep GPs, on the other hand, their aim is to combine this representational power of deep neural networks with the ability of Gaussian processes to increase in complexity as more data is observed, and also to, again, be robust to overfitting in the case where we have small data sets. So what is a deep Gaussian process? Well, it has a similar structure to a deep neural network. If you remember, a deep neural network is basically a composition of functions where each function is made up of a linear transformation and then a nonlinearity. So basically you have your input, then you have a linear transformation, nonlinearity, linear transformation, nonlinearity, et cetera, to as deep as you want to go to your output layer. And we're going to do the same kind of thing with Gaussian processes, where we basically just compose Gaussian processes on our input. So each Gaussian process is drawn from a GP with a specified kernel. I didn't mention, but often we use GPs with mean 0. You can choose whatever mean you want, but essentially mean 0 is usually, that assumption works pretty well for us. So in most of the work we're going to be doing, we're going to be using mean function 0, but we do need to specify the kernel. And then we just stack these GPs. So we get an input. Here's a diagram, an input, and we apply a GP to that input. We get some new output, which becomes the input to the next layer. And again, these are all vector valued functions here. So another idea that we're going to need to consider for what we're going to be discussing later is stationary kernels. And stationary kernels, so let's first say that the kernel determines the nature of the kind of functions that we can learn from the Gaussian process. So again, it's going to be very hard to, if we have a very strong prior for a GP with a particular kernel specified, it's basically placing mass in the space of functions with those properties. So it's important to specify a good kernel, like for your particular problem, and it's going to determine the nature of the kind of functions that can be learned by that GP. And so one particular type of kernel is called stationary or shift invariant. And basically what a stationary kernel means is we can write our kernel, which is normally a function of two values, as just being a kernel which is a function of the difference between those two values and 0. So, we could introduce some new variable, which is this difference, and say, well, our kernel is actually a function of only one variable, which is the difference of those two initial ones. And what this does is it basically says that, if your kernel is stationary, then the covariance between your outputs of your GP, f of t and f of t prime, only depend on how far those 2 points are apart. So it doesn't actually depend on the location of those values in your space, but only the difference between those two locations. Now, just quickly, I want to go over a couple of theorems. We're going to just present them without proofs. And they're going to be the two main tools from spectral theory that we're going to be using, which are Mercer's theorem and Bochner's theorem. So I'd like to talk a little bit about tools from spectral theory that we're going to be using in the next couple of talks coming up. And these theorems are available in the course notes we've provided, but I basically just want to give you a overview of what they're saying. So in Mercer's theorem, basically it says if we have a kernel that defines this positive definite map here, then if we look at its normalized eigenfunctions and associated eigenvalues, we can decompose our kernel as an infinite sum of these eigenfunctions and eigenvalues. And why this is important to us is we can basically view these kernels as maps from our data to some feature space. And we're defining the kernel or the covariance of our function as an inner product in this feature space, the infinite sum of these inner products. And another interesting thing that we can do, we're going to look at next time, is, of course, if we truncate this infinite sum, then we get an approximation to our kernel. But if you want to look in more detail at this theorem, I'll direct you to the course notes to check it out. So we'll also be using Bachner's theorem, and it basically says that if we have a stationary kernel K, it says a kernel is stationary and continues at 0 if and only if there exists a non-negative function, which we'll call the spectral density, such that basically this says that the kernel is determined by its Fourier transform. So one thing that I haven't really mentioned, we've talked a lot about the benefits of using Gaussian processes, but there is a large downside, which is that GPs have an order n cubed computational complexity, where n is the number of observations that we'd like to condition on. So, of course, if we have very, very large data sets, this becomes slow to compute. Things on the order of, say, 10,000 data points become pretty slow, which is contrary to neural nets, where we know with very large data sets, they're still pretty fast. So one of the things we're going to look at next time is the way in which we can use tools from spectral theory to construct an approximation of a Gaussian process, so to hopefully retain a lot of the good properties that a GP has, but that's much faster to compute than the original Gaussian process. Thanks.